A golden dataset is only useful if the labels agree. Cohen's Kappa shows whether your LLM eval labels are reliable before you trust them. You'll learn the shape of a workflow that scores judge agreement with Cohen's Kappa and flags readiness against your bar. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Human label reliability is a very practical choke point. You can build the smartest model, but if your human labels contradict each other, your evaluation is meaningless. Teams reach for reliability checks when they need an honest gate. You want a dataset you can trust for model comparison and deployment decisions, not just a pile of examples with noisy votes. This matters whether you run a quick experiment or a formal regression test ahead of a release. At a basic level, we want two things. First, how often do labelers agree outright? Second, how much of that agreement could be chance? Cohen's Kappa answers the second question by removing the luck factor. A high Kappa means judges are genuinely aligned. A low Kappa means more training, clearer prompts, or a relabeling pass. We will build a compact pipeline that starts from a few labeled prompts and ends with a go, no-go decision for using that dataset in automated evaluation. You'll see naive agreement, the chance-adjusted Kappa, per-topic weak spots, an experiment with annotator confidence weights, and a simple release gate. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. First, we construct the tiny labeled table and compute the raw agreement so we can see how naive numbers behave. This snippet assembles 8 prompt checks and reports the naive label agreement between labelers. The rows pair a topic with labels A and labels B, so every downstream calculation starts from the same ground truth references. By unpacking to topics, labels A and labels B, you get named sequences for later analysis without copying or mutating the original tuples. The generator inside agree does the direct comparisons, and agreement rate makes clear how deceptively high simple agreement can look when evaluators share biases. Seeing naive agreement equals 0.75 in the output shows how a raw rate can hide systematic disagreement risk. Now we convert that raw rate into a chance-adjusted score so we know how much to trust the agreement. This example applies scikit-learn's Cohen Kappa score so you can compare naive agreement against a chance-adjusted metric. Because labels A and labels B are categorical strings, Cohen Kappa score handles encoding for you and focuses on the probability of random matches. Storing Kappa and computing naive gap equals agreement rate minus Kappa makes the penalty visible and easy to log. The printed Cohen Kappa equals 0.56 and naive gap equals 0.19 show that agreement drops 19 points once random overlap is removed. If the overall Kappa looks weak, the next step is to find which topics drag it down before you waste relabeling effort. This code loops through each topic and recomputes scikit-learn Kappa so you can rank agreement weaknesses. The sorted set topics loop gives a deterministic order, which helps when you paste these Kappa rows into dashboards. Inside the loop, IDXS captures row indices for the current topic, so both label arrays feed only the relevant slices into Cohen Kappa score. Storing each result in topic Kappa creates a mapping you can merge with prompt metadata or audit trails. Picking weak topic with min highlights the segment to relabel or retrain first. The output weakest topic equals quality, with Kappa equals 0.50, points to where correction is needed before scaling the test suite. Once you identify the shaky rows, you can reflect annotator certainty in the metric and see what forgiveness those notes buy you. This snippet assigns per row confidence weights and recomputes scikit-learn Kappa to see how downweighting shaky labels shifts the score. The confidence list lets you encode annotator certainty without changing the original labels, which mirrors the notes many review tools already capture. Passing that list as sample weight tells Cohen Kappa score to treat disagreements on low trust rows as less damaging to weighted Kappa. Computing lift alongside the main value captures how much forgiveness the weighting introduced, so you can log the delta explicitly. The printed weighted Kappa equals 0.79 and lift equals 0.24 demonstrate how much the confidence adjustments rescued the agreement score. Finally, wrap these checks into an automated gate that a regression suite or a release pipeline can call. This example wraps the aggregated metrics into a simple shipping gate that protects your regression suite. The isReadyForEval helper takes weighted Kappa, the topic Kappa dictionary, and a target floor so you can encode your release policy once. Baking in floor minus 0.25 for the topic check gives smaller segments breathing room while keeping the overall bar at 0.75. Storing the Boolean in decision before deriving status keeps the branch easy to audit in a notebook or pipeline log. The output dataset status equals approved. Overall Kappa equals 0.79 confirms this weighted dataset clears the go or no-go gate. In this compact flow, the checks run on 8 prompts and 2 labelers, but the same logic scales to larger suites. Instrument these metrics in your labeling tool or CI. Push Kappa trends to a dashboard, and use the weakest topic list to prioritize relabeling batches or to tighten your auditor instructions. Quick recap. We built a small workflow that moves from naive agreement to a chance-adjusted Kappa, added per-topic diagnostics, tried confidence-weighted scoring, and wrapped it in a simple release gate. Use this before you trust a human-labeled LLM eval set for comparisons, or before you bake labels into automated tests. One caveat: weighting can raise your overall score, but it can also hide systematic bias if you overuse low weights instead of fixing label quality. Next step: tune the confidence weighting strategy or the release floor, and watch which topics fail the gate. Try moving the floor up or down, and observe the trade-off between evaluation precision and the relabeling effort required. If practical, hands-on AI engineering helps, subscribe and watch the AI engineering videos.